Today's speaker is Dr. Shih-Chieh Kao. He came to ORNL in 2009 and currently is a distinguished research staff member and group leader of the Water Resource Science and Engineering Group in the Environmental Sciences Division at ORNL, and also the program manager for the ORNL Water Power Program, which oversees various research projects supported by the Water Power Technologies Office of the Department of Energy. He holds 3 degrees in civil engineering, a BS and a master's degree from National Taiwan University, and a PhD in 2008 from Purdue University. His research areas include high-performance computing, hydrologic modeling, flood simulation, hydroclimate impact assessment, and hydropower resource evaluation. And I first became acquainted with him at ORNL when we were involved in a project for the Nuclear Regulatory Commission to investigate severe flooding, which is highly related to his topic today. I'd like to turn things over to Shih-Chieh.
Thank you. Yeah. All right. Okay. Well, first of all, thanks, Alan, and thanks everybody for inviting. It's good to see a lot of people here. I appreciate for this opportunity to catch up. So I'm Shih-Chieh Kao. You can either call me Shih-Chieh or call me Kao. Right? I don't know if Alan remember the story. I have a standard introduction in the laboratory for some reason. For those people who study in climate change, usually call me Kao. And for those people study in water power, call me Shih-Chieh. And so you can pick whatever you want. And also for some reason, my Taiwanese friend, and only my Taiwanese friend, call me Melvin. So if you're interested to use a name, you can call Melvin as well. I know that's me, all right? So today I'm going to talk something about flooding. I think everybody has been telling me I pick an interesting timing to deliver this talk. Definitely I did not plan for what happened in Sunday. But I don't have the slide just for that, but we can chat more. I can share my understanding on that. So this is a multi-year effort we have been doing on the flood simulation, particularly using high-performance computing. So to kind of start this presentation, I bring this up. So this is a $1 billion disaster map that NOAA have been doing. I think they are going to stop it, unfortunately, but they have been doing that. And so as a comparison, this is a 2012 map versus a 2024 map, right? And so you can clearly see that there are more and more $1 billion event, right? Of course, this $1 billion event, it is also inflation, right? Maybe it's just through time you have more and more expensive event, right? It's a nature. But clearly you can see that many of the events are caused by flooding, right? So that's an important reason to study this. So why are we seeing more flooding, right? I mean, one potential reason is climate change, right? Either you believe it or not, but in theory, it is one main driving force. When atmospheric become more warming, more warm, it has a capacity to hold more water, and so that's why you will see more extreme event. Likely see more extreme event, right? Anyway, we would like to do something to better understand. Right. So to model flood, this is some major component. I'm not sure how many of you have a background for hydrology. So just to quickly tell you, these are the major thing. All right. Of course, you started from precipitation. You can either use observation or you can use model to do that, right? Then you feed that precipitation into a hydrologic model system. That's mainly converting precipitation into something what we call runoff. That kind of deducting all the evaporation, losses through infiltration, etc. So it is runoff. It's basically the main thing to cause flooding. Then following that is a stream flow routing. It's basically a process that calculating how much stream flow is resulting from that runoff in each of the river segment. And the final step, which is what I will spend most of the time today, is hydrodynamic modeling or inundation modeling. So basically, this step is started looking at corresponding to the runoff in stream flow. What is the surface inundation look like? This part is basically the computational bottleneck. Most of the computing time will spend here, right? Okay, so fortunately, we do have good big computer in the lab, so we kind of started looking into this. I will show you the timeline later, but this is a model you'll hear more and more today. It's called TRITON. It's two-dimensional runoff inundation toolkit for operational need, right? I like this acronym. We spent 82 hours debating and come up with acronym. I'm proud of it. It was created before ChatGPT, so it's really just manual effort, right? So the goal of this model is basically the main tool we are converting runoff and stream flow to inundation by solving the 2D shallow water equation. So it's basically the physics full form of the simulation of the solution. It's very computational intensive, but fortunately, by using GPU, it's basically the gaming card initially used to help you have a better gaming experience. Right now, people use more and more on that to accelerate computing, either AI, machine learning, or others. And in this particular case, it has been found that by using GPU, one can largely accelerate the solution of the shallow water equation very, very quickly. So we have been spending time on that. Another unique thing for TRITON is that it can solve both pluvium flood and fluvium flood, right? So what that means? Fluvium flood is the flooding you only consider the river. So it's a river flood. Pluvium flood occur when you have heavy precipitation occur, right? Like for Texas, that's more like pluvium flood. So TRITON doesn't have the capability to solve both of them, right? Okay, so we designed TRITON in a way that is very easy to use. At least we think, all right. For the input data, we basically need digital elevation. So it basically, that is also serve as a computational grids, right? So we typically use 10-meter resolution DEM over 30, or if you have higher resolution DEM, we can use that too. We use a parameter as the water input. We can either input the water as the stream flow, or we can input the water like a runoff. So it's just two different ways we can set up the input. Then the model will distribute it to different GPUs, and we can do acceleration on that, eventually come up with the output. And TRITON output generated depths and the velocity of both directions. And so that is the main output from there. We are fortunate having this opportunity to start this project through the support from Air Force. And so we started back in 2019. And at that time, we have some foundation called Flood to the GPU. That's from Tennessee Tech University. We at the time can use 12 GPUs to do acceleration. And so we have some early study looking at in a selected region how things could look like in terms of flooding. And so like on the right-hand side, it is the HUC 8 level watershed. If anybody know HUC, you probably know that. But how small it is that if you see there's a small map there. Okay, thank you. Right. I'm not going to click that again. Right. I've just come here. So see this map? This is how small this watershed is. Right. Okay, so we start trying to spend some time trying to expand it. The idea is that if we can kind of make it larger and also improve the efficiency, then that can become more useful when we use that for operation type of thing. So Hurricane Harvey became one important milestone for us. This happened back in 2017. And one unique thing for Hurricane Harvey is, if you heard the term called probable maximum precipitation, that's basically an estimate created by NOAA, tell you that physically speaking, it is a certain location. What is in theory the maximum precipitation that may occur? Right. The unique thing for Hurricane Harvey is this is the very first time the actual precipitation actually exceeded that threshold. That should not happen at all, but it did happen. Right. And for Hurricane Harvey is also an interesting case is that it moved very, very slowly. So you have a hurricane there, it kind of stalled there on Houston for several days. That's why it's caused so much damage. And there's a slow moving feature of what just happened this weekend for the Texas flood is kind of similar. It's just when the conditions are there, it is possible for the storm to move slow, so that they dump a lot of water. Yeah, and that becomes a problem there. So we kind of scale up this simulation. So we end up use 384 GPUs to solve it. And so this is a chart there. First of all, by using GPU, you can already provide nearly 100 times speed up when comparing to one CPU. And here, by using more and more GPU, we can even cut down this simulation to, at the end, around 20 minutes. So we can solve this huge simulation in 20 minutes. And if you use one CPU, that's will take you more than several days to do that, right? So then we still keep scaling up. So we start to do it for other hurricane, and our domain size has been increasing. So there's a number you see under each of the event. That's count the number of grid cells. Because our model can be applied to different resolution. So it's more useful to count it by number of grid cells you can solve. Right? And the higher the number, that means you can solve more. And for Hurricane Sally, we already pushed it to 1.4 billion grid cell. And then we come to the first challenge, unexpected challenge. Kind of stuck at 2.1 billion grid cell. And the reason is when we initially designed TRITON, we did not realize we will go that far. And so we declare some certain variables as a regular integer. And so for that, you can only go up to 2.1 million, right? So we go back to revise the code to make it a long integer. We finally expand that, but that's the very first surprise that, okay, we never realized we can go that far. Right, so we keep pushing on that. So then the next one I would spend some time to talk later is the Missouri River Basin flood. It's a very huge area over, you can see. We start by looking 30-meter resolution, DEM, that's a 3.3 billion grid cell, can do it. Then we start to encounter some challenge, all right, out of memory. So we end up creating a parallel IO feature to do it in TRITON. Then we push it to 30 billion grid cell. And 30 billion is an important step because at that time, we finally are able to use 20% of the summit, which is the threshold for leadership computing. So we finally reached there. We qualify for inside application. So that's an important step there. Right, so talk something about this flood. This is a 2019 midwestern flood. This is a very unique flood as well. It actually lasts very, very long. 5 months, right? And so what happens is that you have done a lot of precipitation, snow melt happening entire Missouri River Basin, which account for around 1/3 of the United States there. So at the end, this becomes a very amazingly large flood. So there's an Air Force base there. So if you compare the March 2018 to March 2019, image, you can see that a huge area got flooded there. Right, so computing wise, this also represents so far the largest hydrodynamic simulation for inundation, right? To our knowledge, right? So basically, what we have been doing here is instead of doing it in hydrologic modeling sense, we do it in hydraulics modeling sense. We take its entire region. We first start by using the 30-meter resolution DEM, 3.3 billion grid cell, then move it to 10 meter resolution grid cells, which is 30 billion. We run it for 5 months. It's a very, very long simulation. And for 30 meter, we were able to use a big chunk of a summit, and we finished this long simulation in 1.5 day. And for 10 meter, we were able to push it to 6,000 GPUs, to 20% of summit. And we can simulate this 5-month simulation in around 2-3 days. Yeah. So that's kind of more like a demonstration about how much we can go. Operationally speaking, we probably don't need to do that because you can consider there some reservoir in between, there's some water control. It's probably more logical to break it into smaller model and link it together. And so you have a reservoir component in between. But this is more like a demonstration about actually we have the capability to do the big run. Right. So we have been doing some evaluation, and so far it looks very good that it can capture those flooding event and still have a good, reasonable performance. It's exactly what we want to see. All right. So then at this point, we have kind of demonstrated the capability. But sadly, Summit is going to decommission. This is end of lifetime of this good friend, and we are moving to the new era of frontier. Right. So we spent quite some time. It's actually much challenging when we thought because originally we wrote the code for CUDA using CUDA for NVIDIA GPU, and that's available on Summit. But when it comes to frontier, it is an AMD GPU. And they don't like CUDA. They have something called HIP, right? So we need to spend quite some time there. And there's actually an interesting program they provide. It's called Hipify. So we kind of Hipify all the CUDA code so that it can run. On Frontier, but it worked out. So we do that. We also made some progress to set up a ensemble run. But basically now we can run a lot of storm we want to see all together. And so we were able to eventually push it to use 95% of Frontier. And that big simulation was done using 72,000 GPUs. So that's quite amazing. But at the same time, we still were able to keep good scaling over there. And what we learned is when you move IM up, you do need to have a large domain to show that. But anyway, I'm not going into the detail today about that part, but if you're interested, I can provide a paper. If you still want to read the technical paper for computing, I'm happy to provide that. So talking about the next steps. So this is what we call TRITON V2. So why V2? As I mentioned, when we started to do this code using the NVIDIA GPU, it was written in CUDA. Then when we started to use Frontier, it's on HIP. And now we also have access to Aurora, and Aurora uses Intel GPU, which is totally different. So we cannot go on like that. So there's a better thing, it's called Cocos. So Cocos is more like a cross-platform type of tool. So we end up picking that up. We kind of use Cocos to drive TRITON code, and it worked out, and with a good performance. So starting from V2, we will basically build TRITON on Cocos so that hopefully you can just be able to adjust to different GPU cards. And hopefully that will be a better thing for the user. Okay, so that's on the development side. I want to talk about some evaluation application of TRITON. So we have been working with some external collaborator as well, and this is the paper they just submitted, and there's a preprint. If anybody interested, they can see the comparison. In this comparison, they basically use 5 different inundation model. TRITON. Then there are 2 more also hydraulics level model. It's called Flood MP and HECRAS. And also they use 2 very quick mapping tool. It's called AutoRoute and HAND. They do the comparison, and they found a good performance of TRITON and apart Flood MP and HECRAS. So the upper 3 model basically they try to solve the shallow water equation, so they can have better performance. The follow 2, this 2 model here, AutoRoute and HAND, is what we call terrain-based model. So they basically use a lookup table to quickly tell whether they could be flood or not, and that's generally did not work so well. So not a surprise, Triton will work well. Otherwise, I would be very disappointed. We spent so much effort there. But most exciting thing they tell us is that for the simulation, Triton can run within half hour. They spend time to run is to HECRAS and took them 17 days to finish it. And HECRAS is currently the engineering model that people will use, right? So that's a good motivating factor why people should consider using a new model for that. Right. So what we are also trying to do right now is we start to setting up Triton for different watershed. So the idea is that once we're ready, we will create a portal so people can download the pre-staged parameter, and so that they can cut the piece they want to do the modeling they need. We will do it for some corners, and we may do it for some important global watershed. And during the development of this, it will also give us a good opportunity to evaluate some historic flood. So this is some example, like in different watershed there, we kind of pick up some major historic event and use the observation data we can get and try to evaluate and calibrate the model. I don't have a slide further, but I also want to quickly mention another thing to doing this type of study is it is really, really hard to find data to calibrate and validate your model. Right, it's hard. I think right now people recognize the satellite image is a good thing you can use to validate, right? But many of the satellite image will also be affected by cloud. And guess what? What will happen when there's a flood? It's a cloud. So actually, it's really hard. Sometimes it's that's a problem. We spend so much time trying to calibrate the model on that, right? Anyway, so apart from that, I also want to mention this is an ongoing effort, but the idea is that okay, great, you guys speed up Triton, but still, this is very computation intensive. If you're going to do operational forecasting, how are you going to do it? Right. So what we're trying to do is we're trying to develop an AI machine learning based surrogate model, what we call TRITON Lite. And so, but the goal is if we can create a surrogate model that only takes 10% of the computing, but you can reach 90% of the accuracy, then that should be good enough, right? And that's our goal. Still ongoing, but we do have some initial result to show that, hey, this concept should work. So in the following few years, we'll kind of keep exploring that. So eventually it can be a hybrid case that we use the AI machine learning surrogate model to do the first guess of the flood forecasting. And for region that exceed a certain threshold, then we will run Triton for those region. So that's the plan for that. Right. So another thing I want to mention today is probabilistic flood inundation mapping. Right. When it comes to flood mapping, I think people may heard the FEMA. That's where you can get most of the flood map. Right. But the problem for FEMA is that the flood map, first, it does not available everywhere, and most of the places you couldn't find one. The second is that that map is not updated frequently, and usually it's based on some very fixed assumption, right? It may not be that useful. FEMA flood map is usually only considered as the minimum standard one can meet, right? So there's a need to have a more flood map. And what we are trying to do here is that we have a very efficient flood model, and we're trying to explore how to use that model to do probabilistic flood mapping, right? So what is the idea of this probabilistic flood mapping, or called ensemble flood map? It's basically now conventionally what people have been deriving, they say 100-year flood map. What they did is that they go to each river, they analyze what is a 100-year level stream flow, and they use that stream flow to drive hydraulics model to get a flood map doing one run. Because as I mentioned, hydraulics simulation is the bottleneck. When you no longer have a bottleneck, what you can do is instead, I'm not going to estimate 100-year first. I'm going to go to each of the year. I'm going to pick the annual maximum. I'm going to run each of the flood map. So what you end up have is at this location, you have hundreds of thousands flood map, all corresponding to a certain annual maximum event. Then at each pixel, you can then start to do flood frequency analysis to derive what is the flood estimate. So that's the idea. So this is support we have been trying to do it for several locations, trying to prove a concept that. Right. All right. So this is a example location that I'm going to show today. So what we've been doing here is we first use a downscale and bias corrected climate projection as a driving force, right? So in this case, in each climate model, they did provide a historic baseline, and that is more like a stone generator in that sense. So for each climate model, we use a historic baseline to run the flood map, and then we also use a projected future condition to run the flood map. So here, represent the name of the 6th climate model we select. And the blue box is a historic condition, and red box is the future condition. So each of the model tells us that you're likely to see an increasing flood zone in the future, right? And that the bottom line shows the projected increase of the flooded area. Right. So here, the lighter blue is more like a baseline, and the red, the deeper red is the one that increases the region in the future condition. Right. So this is a different way, and here you start to see this is probabilistic information. So this is the historic condition, basically using the hydrologic condition from 1980 to 2019 to run simulation versus use a projected future condition from 2020 to 2059 to run the simulation. And here represented to the probability of flooding, and you can see the deeper red means higher chance to get flooded, and vice versa. You can see the increase from historic condition to the projected future condition. This is a different way to look into it, and this way that we focus on 1% flood. 1% flood is actually also called 100-year flood, depending on how you're going to look into it. And similar thing that you can see that a general increase of the 100-year flood in this region. And this is a different way to look into it. So first, over this size, it shows the change in 1% flood depths. And in most of the places, you do see the increase, projected increase in flood depths from the historic past to the future. And on the right-hand side is a comparison with the FEMA study. So for this particular location, they did not initially have FEMA study. They did a FEMA study because after the major event happened in the region. And so that causes another problem with FEMA's flood map is that it's not always available in any places. Yeah. All right. So this is just a show some example layer, but hopefully you can see the idea how the model can be used. Right. So this is a final example I want to show. It's about Hurricane Helene. So when Hurricane Helene happened, we also want to test it how TRITON can be used on this case. So in this case, we take a different strategy. We look at entire domain layer as our computing domain, and we use TRITON to simulate everything. And so we set up a simulation for a 10-day period. And in this case, it's 30-meter resolution, and we simulate this entire big domain on Air Force supercomputer called HPC-11. It takes over 11 hours to finish that. So we started to look into the performance of the model. This is one part of the evaluation. In this case, is Asheville. So I'm sure everybody have been there. So hopefully you can still remember and look into that, have some know where it is. So like if you look at Wendy's is there, on the map is over here. And that building is actually over the box there. So in general, by just using this historic, this is using this news imagery, and you can see that, hey, actually you kind of capture some flood region there. We are conducting more detailed evaluation and also trying to improve the resolution now. So this is the initial round. We did it in 30 meter, and right now we just finished a 10-meter resolution round. So we'll be able to see a more detailed analysis later. Another team member is trying to look into the simulation and in different region and try to compare. In this case, he used a heat rate to see that, hey, how much heat this model captured. Hopefully, one day we can kind of make this thing operational, right? So that we can provide information before the storm occur, but before the flood occur. But at this point, we focus more on reanalysis after the storm occur. All right. Overall speaking, this is what we learned so far. We have a model, but right now, the other thing is the data size is really crazy. It's really great, easy to create terabytes of data, and it's really hard to figure out how to handle it. So one of our future research will look into ways that we can compress or keep the data. Getting data to validate is very difficult. I just mentioned about the satellite image, right? So this is a continued challenge we will have. The other thing is digital elevation, which is surface important baseline for the model. It needs some correction. For those of you who may have not used digital elevation data before, many of the DEM, they only reflected to the surface elevation, not the bottom elevation. And that is a problem because we actually need the bottom elevation to run the model. So that's a certain thing we need to study as well. Flow regulation is a big one because we are very fortunate we're living in the Tennessee Valley here, and TVA already did amazing work trying to help us to control the flooding, right? But in terms of modeling, what I mean is if we want to capture that, we also need to embed it with the reservoir model. So that's a certain thing we need to look into is how to include reservoir operation into type of this modeling framework. All right, and other software challenges as well. All right, so in conclusion, this is some final summary here. I hope today you are convinced that there is a need to look into using GPU to accelerate flooding, and maybe one day we can use this more and more in operational sense. TRITON is what we created. It is also an open source tool that for those of you who want to use it, feel free to use it, no string attached. But that's what we have been trying to push people to do that as well. Just use it and let us know how you feel. Right now we already demonstrate we can do a huge dynamic simulation for around 1/3 of the country. I think we're not too far that eventually we can do this operationally for the entire US. And hopefully, if the funding support remains stable, if everything goes well, hopefully by the time I retire, I will be able to do that. We'll see. Still 11 years to go. All right. Okay, I think that's it. I try to save some time for discussion. Yeah. You want to moderate or?
I go just.
Yeah.
Yeah, you go ahead. John.
In the days before levees were common along major rivers such as the Mississippi and Missouri, our perception is that the floodwaters would spread out over a larger area and you wouldn't such have a high flooding downstream. But with the introduction of levees, it's pushed a lot of that water, high water downstream. Is there any work in your computations to evaluate perhaps removing levees in areas where it might spread out and this minimize the downstream flooding?
Yeah, that's a great question. In fact, yes, that's exactly the type of thing a model like TRITON can do. And the way we can do it here is by modifying the DEM, digital elevation, right? Like basically you're modifying the levee, like you remove it, to run a model to see how it look like or make it higher and to see the impact, right? In fact, another thing TRITON can do, which I did not show anything here, is actually dam break. You can also suddenly remove a dam to see how the flood will propagate and impact in a very short time frame.
Have you had any such recommendations along those areas yet?
No,
No.
I mean, we don't have a sponsor yet, so no, I don't have any recommendation yet.
Ray?
I never heard you mention rainfall. Would the ideal program be one that starts with rainfall and predicts flooding from that point?
Precipitation.
No,
We use the term precipitation, but yeah, it's rainfall. Yeah, and the other thing is runoff. So yeah, there's so many different terms here. This model is called two-dimensional runoff inundation kit to toolkit. So what is runoff? Another way runoff is also called effective precipitation. It's basically now when you have precipitation, after you look at how much loss it is, and those things, the remaining part, the remaining excess precipitation, how that will become flooding. Right. So yeah, it is definitely tied into rainfall. Yeah.
Kent?
Do insurance companies use models like this and try to predict what areas might be most prone to flooding and therefore higher premiums?
Yeah.
Can you repeat the question?
Oh, okay. So the question is, does an insurance company also use a model like this to calculate the premium? So the answer is yes. I mean, they do not use exactly this model, but they use other model on the market. They have several similar other model, like HackRAS is one of the most popular model there, but there are also other type of commercial model people have been using. So there's a big industry trying to look into how to adjust the insurance rate for that. And it's unfortunately, I think people realize it's become more and more expensive. And I'm not sure if we will eventually go to a point that it's too expensive. If it may not, nobody can afford the flood insurance anymore.
Rich?
You showed the graph of the 6 models and the current and future flooding. 5 of them look pretty similar, but one of them showed no response. What's different in that model? Is there some critical assumption that's different from all the other models?
Okay, so the question is about the 6 model I showed. So there's one model showed the relatively smooth projection, right? I think, of course, we can look into particular model to see why it happened there. But in general, what we learned so far is there's a huge variability into the model projection, right? Because each model, although you feel like you have longer period, but for this type of flood simulation, just one model projection is not enough, right? And so the more the better. And here I think we found a trade-off is that use 6 model and jointly, some model will give you higher, some model will give you lower, but by looking at the ensemble behavior across all model, hopefully it will give you more confidence.
Similar to the hurricane projections, I guess.
Yeah, similar to hurricane projection, as you mentioned, right? And the other thing to mention is when I'm talking to some people, especially some civil engineer or some user, that's a very common question. They just say that, so can you just tell me which model to use? And I need to explain to them, no, you need to use many models.
Fine, you'd say.
Yeah, but they say that, yeah, okay, but I understand. But can you tell me which model to use?
But you can usually learn something by figuring out why one model differs from another. Right?
Yeah, so yeah, the question is, can we learn something by looking into a particular model? Yeah, I think we can, right? But it's very complicated as well, right? Because of 6 model, different region, each model have different response. So it would be nice to look into that. There's an R&D thing we can look into it, right?
John?
But a lot of coastal flooding is dominated by, wind-driven surge and tides. Do you look at those things or you're looking only at rainwater runoff?
Yeah, that's a great question about the coastal flooding, because when it comes to coastal flooding, certainly the downstream surge is a thing. So our model has the capability to set up downstream boundary condition. So basically in downstream boundary, we can give a water level so that we can simulate that, okay, by having this water level, how will they look like in terms of flooding? A more involved way will be dynamically coupled TRITON to a storm wave and surge model. That's a research thing. We are working on it now. I don't know how soon we can get it done, but yeah, that's possible.
Steve?
Yeah, we have a Zoom attendee who asks, would synthetic aperture radar, so-called SAR, pierce the cloud cover? There are commercial open source SAR satellites in orbit now.
Out of my expertise to answer that, but yes, I think it is possible. I think they are very different satellite product, and I think my team did use some certain product to help to evaluate. But still, I think it is challenging because the radar also, each satellite also has its own interval scanning. So it doesn't mean that at the time we want, it has the image we can use for evaluation.
Jack?
You said TRITON is open source code.
Yeah, the question is, is TRITON real the open source code? So yes, it is open source. As on the link.
What are the
Yeah.
equipment requirements for the digital computer requirements to run TRITON?
Okay, what's the equipment needed to run TRITON? We designed TRITON in a way that actually you can use CPU to run it. You can use multi-CPU, multi-GPU. For the best application, we will recommend you to use a GPU, right? You don't necessarily need to use supercomputer, which has hundreds of thousands of GPU. If you just want to look at a small domain, which have a less number of grid cells, and you have only one GPU, it's totally doable. Our sweet spot right now is I will recommend for each GPU card is good for 10 million grid cell. Right, so if you just set up your domain wisely, then yeah, just one GPU card you can do it.
And where can you get the code?
It's on the link.
Okay.
Yeah, it was send me email.
Steve?
A Zoom user asked, do you or have you worked with or interfaced with the Defense Climate Assessment Tool, DCAT, used in DoD to quantify hazards to military installations, domestic and overseas, in 2017?
That's a great question. So I would say the short answer is yes. But first of all, we don't have access to DCAT. And right now it's called DECAT. They changed the name as well. But we have a close collaboration with ERDIC, which is the Army lab. They have access, and we are trying to explore how to kind of, because they are using auto route. So we basically, it's a collaboration. We're looking to TRITON versus auto route and how to combine it together type of thing. Yeah. Yeah, I think DCAP right now is not open to the general public. So we do want to log in there to see where they are right now, but I don't think we can get in at this point. But yeah, another thing I want to mention is because this was supported by Air Force, so we certainly is in that community. So yeah, we are talking to them. Yeah.
Yes.
You mentioned when we started out that you'd say something about the tragedy that's happened in Texas. And rather than ask a direct question, I'll just open it up and say, what are your comments?
And I need to be careful because this is recorded. So I was from Taiwan. So if you if you know what I mean is basically a small island, but it's very hilly. So for us, we know it is very dangerous to go close to any river, especially after thunderstorm, because it may be very sunny, but you don't know what happening upstream, right? And we already see some similar thing happen like that. You see over 26 feet of flood just coming, right? I just did not realize this thing could also happen in Texas. And I think that's a surprise. Meteorologically speaking, I think I'm not a meteorologist. I will hope meteorologists to analyze it and let me know what really happened. But what's unique for this storm is that actually small lasted. It's kind of stand there for a while, dump a lot of water, and that's why. When at a certain occasion when you suddenly have a lot of precipitation, the thing can happen, right? Yeah. So sorry, haven't analyzed it, so cannot say too much.
This is related to that and a little bit related to Ray's question. My understanding of the Texas situation was predictions were for 5 inches of rain in a 24-hour period, and they got 20 inches of rain in a 24-hour period. Would your model, therefore, for emergency preparedness said, okay, if you get 5 inches of rain, this is going to happen, but if you get 20 inches of rain, that is going to happen?
So several things for that. So yes, I mean, if you're talking about emergency preparedness, usually that means you pre-run a lot of different scenario. And so it's not just one scenario, you have worst case, right? So by running a different scenario, you will be able to see that, okay, under certain worst case scenario, you may see this great impact, right? If you already done that for a certain occasion, you probably have an idea, better prepare yourself. But when it comes to forecasting, that's really, really hard, right? I mean, so far, I don't think people can forecast rainfall depths in particular accurately, right? So let's say focus 5-inch versus 20-inch. I would say that actually doesn't sound bad. Yeah, because I don't think people right now can precisely forecast 20-inch. We are very, very far from that point. Yeah.
Jack?
Just a follow-up to that, though, you implied with your model that you could look at the 100-year flood as a 1% probability flood, and that you have looked at various PMPs, probable maximum precipitation. Is the model built so that you can put in those numbers and give a run on it, which would at least seem to give you some ability for, if we get the 1/2 PMP, how long can you tread water?
So yes, the short answer is, if you kind of remember in the beginning, I showed the 4 different components, right? So we intentionally stay at the corner in a way that we don't have our own hydrologic component. Instead, we can take the output from any hydrological model to plug into run TRITON. Right. So whatever hydrological model one may be using, like maybe it's a Sacramento model, we use big model, or there's a national water model. As long as this model provides the reasonable runoff with stream flow, and then we can use that to drive TRITON. Right. And those model, then by using that, you can give different precipitation input. You can give a PMP scale if you are interested to see the biggest event, or 100-year rainfall, or an ensemble of a big data set. You can do that, and TRITON. The goal for TRITON is that, okay, now assuming this is the runoff I'm looking at, try to convert it to flooding very, very quickly. Yeah, so that's basically what TRITON has been doing.
Steve?
You have found that each supercomputer needs different code. Do the conversion programs yield as good results as the original CUDA programs?
So the goal for going COCOS is for that, right? So originally when we wrote TRITON, we used CUDA because that's the time that's the thing I would say that only NVIDIA is a GPU provider, right? So we use CUDA. Yeah, and no surprise, everybody started to do GPU and we need to do different thing, right? But the hope is that once we change to Cocos, they will be able to do that work. They will make themselves available for different GPU. So as long as we follow that, then hopefully we don't need to change on our code. We just need to adapt to Cocos.
Carolyn?
The BBC article on the Texas flood said that humidity coming from a storm in Mexico contributed to the rainfall, which I guess also came from somewhere else, and also the Texas landscape. Is the landscape something as well as humidity that is data put into the simulation?
The question is about humidity and
Landscape,
landscape.
yeah, hills and that kind of
Topography.
Topography.
yeah,
Yeah,
That's what the D is.
topography, yes.
yes.
Topography, yes, because I mentioned DEN. DEN stands for Digital Elevation Model. So it's basically tell you each grid points, how tall, how high it is. And so this model is basically by given a topography, you try to simulate how flood will accumulate if impact certain place, right? So yes, this
And that affects runoff, I guess, the topography.
is we don't simulate runoff. We kind of simulate how runoff will accumulate on a certain topography.
That comes out of here.
Right.
In the recent flood we had here, we had danger of a dam break in East Tennessee. Would your model be able to predict some useful information in case of a dam break like the one we were threatened with in East Tennessee? I mean, that might be useful to say what the consequences might be.
So short answer is yes, and we are doing that. The way to do so basically TRITON is the most initial simulation TRITON have been doing is actually for dam break. It's a townsite dam break. So we were able to do that scale that I mean dam break. But when it comes to dam break, it's ultra sensitive stuff. Is CEII or something. So basically, maybe we are already doing it, but we cannot tell you that thing.
Great answer. Anything else? Okay. Well, we appreciate. You've shown us a bit about how a supercomputer can do things other than AI. That are great value, but it'll be a little while before we have one of these in every weather service office around the country to do this kind of analysis in real time. But we appreciate the presentation, and in honor of your experience with Friends of ORNL, enjoy this coffee cup.
Yeah, thank you so much.